6.4. We are going to spend more time uh, to understand the log function and exponential function. Right? Remember, we we gave the definition, right, for the log function. So if y equals a to the x, then you solve for x, and this should x depends on y, and the notation for this function will be log of y with base a. Okay, so when a equals e to the x, then we use an h log. Okay. Now there is a formula we find out. Remember the derivative of a to the x is going to be a to the x. I remember we mentioned L and A, right? And also the derivative of you can use the y variable. This is going to be 1 over y, L of A. So what is the LA? So mathematicians find out this LA is nothing but the natural log of A, right? Yeah. So this is just natural log A, and so use that. I'm not going to spend time to prove it here, but if you use this, then you get a little bit more specific formula. It's going to be a to the x, natural log of A, and the derivative of, I'm going to use x variable. It's going to be x ln A, okay? Now, another important formula for the natural log is this one. You can use any base, right? In particular, when b equals e, then that will be the natural log, right? Natural log. So this is also in the natural log of x was replace a is not a brand new function. It's just the log function. Okay, log of x with base a is just the natural log of x divided by a constant natural log of a. Okay. So those are the information we need for today's class. And let's take a look at the first example. We are given this function. What do we want to do? We want to find the derivative. How to find the derivative? There are a couple ways to find the derivative. The first method is just use a channel, okay? And this will be more complicated because this is a composite of two functions. One is a natural log with base 2, another one is square of x. So when you find a derivative, remember, right? So this is use a channel. I think this will be 1 over square of x, right? Natural log of 2, and you have to differentiate the square root of 2, okay? So differentiate square root of 2 is this. Okay. I hope you understand how did I get this. I use the following formula. The derivative of y was base a, it's going to be y natural log of 2. So y is square of x, okay? Then the derivative of a square of x is going to be 1 over 2 times square of x. All right. Using this 2 as a channel, and you get yeah, you get this. It's a chain rule. Right, you get that. Then you simplify it, you will get 2x natural log of 2, right? Square x times square x is give me x. So that's not easy. Yeah, sometimes it's, we can easily make mistakes. So I'm going to suggest you another method. Modify, simplify the function first. Right, simplify the function first before you take derivative. I really don't like square x, right? That makes it complicated. So what I'm going to do is I use a formula. Square x is x to the 1/2. And then okay. Right. So you can also express it in the following form: natural log x, natural log of 2 for you. Okay. So all you have to do is just find the derivative of natural log x. Right? It's very simple. Just a 2 natural log of 2. That's a constant. So derivative of natural log of x is 1 of x because, right? We have a simplest derivative. Derivative of natural x is 1 of x. Derivative of e to the x is e to the. Right? All right. So much better, right? So simplify the function first before you find the derivative. And then similarly, you can do the following problem. Right? Right? Find the derivative. So when you're given this problem, look at the function first. Are you able to simplify to the function to the level where you can easily find the derivative? And then when you see square root, right? Inside the log, you can remove the square root radical. So first of all, it's going to be expressed in the power function form. Then it's 1/2 log. Right? I think I cannot simplify it first. Natural log, the log of x squared plus 1, it is, yeah, there's no other formula you can separate. Okay, don't create a new formula. Formula is there, it's given. It's given by the God, okay? You cannot change it, modify it. Mathematicians just discover those formulas. You cannot modify the formula. You can change the expression a little bit, but essentially it should be the same formula. So this, I just want to say this is not going to be natural log of x squared plus natural log, plus log of 1 with base 2. And don't, there's no such formula there. So you have to stop there. Then you find the derivative. And then apply the formula, right? It's going to be, you move x squared plus 1 to the denominator, and you have to multiply by natural log of 2 because the base is 2. Then you find the derivative, x squared plus 1. Okay. And the derivative of x squared plus 1 is 2x. So you get 2x on the top. Right. So that is answer. All right. So I'm going to, after simplify, show all the necessary steps, okay? Because it's not easy to get the final answer correct. So more details you put there, more partial credits you're going to get. So here's a function. Find the derivative. Now, if I put this problem on the final exam, I still see that about 10% of students find the derivative directly without even modifying the function. And they're very complicated, and they use a quotient rule or something like that. Okay? So that means this student did not spend enough time to practice. Maybe I did it in the class, maybe he did it once, but I just forgot. Yeah. So and spend more time and much easier to make mistakes. So I want you to try first, okay? I hope we already defined the derivative and simplified. Now, if you do not modify the function, it's very complicated. Okay, you can view this one as a y, then the derivative by the chain, right? If this is a y, this is a y, right? Then it's going to be 1 over y and times natural log of 10, and then derivative of 1 minus x, 1 plus x. Then you have to find the derivative of this function. You get a more complicated expression, but that's what I saw on the exam. Some students does this way. All right, this is just more complicated. So we are not going to continue this way. So I'm going to modify this function. You get 1 minus x minus natural log, right? And 1 plus x. You see, instead of fraction, you get the difference. Then it's very simple. Okay, and then the derivative is going to be the first one. It's going to be 1 minus x times log natural log of 10. And the derivative 1 minus x is going to be negative 1. Minus the same, 1 plus x, natural log of 10. The derivative 1 plus x is just 1. So you just have 2 terms. Because you don't need to combine them into 1. Not necessary, but you can. Okay. So if you want to combine them, you get a negative sign, right? Both are negative sign. I think the common fact, and you get 1 plus x plus 1 minus x. And the answer will be like that. Okay, see, 1 minus x times 1 plus x is 1 minus x squared. The numerator, just add them together because they have both a negative sign on the numerator. So you take a negative sign out, so you get 1 minus x plus 1 plus x. So that's just give you 2. You see, so simple. You don't need to do lots of computation. If you don't want to combine them into one fractions, that's okay. You still get 4 credits. Okay? Some students just leave like that. That looks fine to me. Okay, that looks good too, right? Right. Sometimes when you combine two terms together, it becomes more complicated, so just leave it. Right? Great. But if you want to directly find the derivative without modifying the function, as you can see that, right? This numerator, the denominator is complicated, then you have to find the derivatives of the quotient of two functions. The more exercise you do, more experience you get. Find the derivative of y with respect to x. Right? Now what? I cannot simplify modify this function. I cannot find the derivative. Right? There's no log there. Cannot. Right? If you find the derivative, what do? You use a chain rule. If you use a chain rule, you still have to find the derivative of x squared minus 1 over x squared plus 1. It's complicated. Right. We have to find a way to solve this problem. All right, what I'm going to do is I'm going to put natural log on, create one. I put the natural log on both sides. Okay, and what? Then I get 1/2 natural log of x squared minus 1 over x squared plus 1, right? Then I can separate it looks better, right? But left-hand side is just natural log of y. It's not y. That's fine. You differentiate both sides with respect to x. Differentiate both sides with respect to x. The left-hand side, what you get? You get the 1 over y derivative with respect to y, right? We agree. Because y is not x. So when you differentiate natural log of y, you get 1 over y by the chain rule and times the derivative of y with respect to x. That's okay. It's simple. Then the derivative of x squared minus 1, you just put in the denominator. Then you differentiate 2x squared minus 1, that's 2x. And the derivative of x squared plus 1, you can also get, put x squared plus 1 into the denominator. It's 2x. Okay. I think we can continue simplifying the expression. I think I'm going to take 2x out. I just say x. Right? And combine them. 2x over 2 is just x. Combine them, I get x squared minus 1, x squared plus 1, x squared plus 1 minus x squared minus 1. Not too bad. X squared cancel out. I get 2. Okay. But that's just this is not the final answer yet. We want to find the derivative y with respect to x. So from the above expression, derivative y with respect to x is 2x over x squared plus minus 1 and x squared plus 1 and times y. So what is y? Y is already given. Y is a given. Y represents the square root of x squared minus 1 over x squared plus 1. Okay, done. Can we simplify this expression a little bit? It's possible because I see x squared minus 1 two different places. Right? And yeah, I think we should put x squared minus 1 in the denominator. So this should be 1/2 as a 1 x squared plus 1, 1/2 3 over 2. Yeah, 1/2 plus 1 is 3 over 2. So that's it. So this is the final answer. All right. So sometimes you have to add natural log to both sides, then you solve the problem. Okay. This problem is a little bit more difficult than previous. And previous one, you just modify, simplify the function. This problem have to be more creative to solve this problem. Then you will question, how do I know that, right? And well, somebody's find out, and we learn that, and we memorize it, we use it. Okay. And when we see similar problems, you know you can put natural log on both sides. Okay. And like y equals x to the power x. Find the derivative with respect to x. All right. So this is not a power function. This is not exponential function. This is a very strange function. Both are changing. Okay. Power function looks like that, x to the power k. Exponential function is a to the x. But x to the x, okay, these two components are both a change. It's not in the form a to the x. A to the x is a is fixed, x is variable. X to the power k is fixed, x is variable. Just only one variable is fixed. There's only one variable there. But now x to the x, when x increases, the power increases too. So x to the x increases much faster than exponential function, just because the base x is also changing, right? So when we try to, let's try to find the derivative. All right. How do we find it? Right, there's no log there. I cannot simplify it further, right? The function cannot be simplified. But this time, we already learned some ideas from previous examples. So we not say we need a creative idea. Somebody already found it. We just copy and try, right? Yeah, we just copy and try. So put the natural log on both sides. It's not so easy to be a creative, okay, but little bit easier to use somebody else's idea, solve the problem. Right. So that is going to be x times natural log, right? Now this becomes a very nice function. Product of two simple functions instead of x to the power x, right? X to the power x is bad function. Now x times natural log x, we call pretty friendly functions, right? Everybody knows x. Everybody knows, right now, everybody knows natural log x. So I differentiate both sides with respect to x. This is just an implicit differentiation. Right? Yeah, someone, maybe was a little bit creative, find this method, then other people can copy and use it. Maybe you learned from other problems, or from the multivariable calculus, and you use that here, right? So it's not necessarily within the same subject. All right, differentiate, that's going to be 1 over y dy over dx. And then here we apply the product rule. It's 1 times natural x plus x times 1 of x. Right, because the derivative of natural log x is 1 of x. And finally, I got natural x plus 1. All right, so I'm done almost. It's the same idea. Times y, x natural x plus 1. And what is x? Y. Y is x to the power x. All right, great. All right, so we solve the problem. All right. Let's recall the formula, right? Net derivative of natural x is 1 of x. That is true for x greater than 0, okay? Because otherwise, natural log x is not defined. Natural log of x is defined only for positive x. So that means 1 of x is always positive. This function is increasing function, but it's increasing a little bit slower because 1 of x is getting larger, and the 1 of x is getting 1 of x is getting smaller and smaller. So if you look at the picture of natural log, then it goes like that. Okay. So when x is getting close to 0, this curve is very, very vertical. Okay, the velocity. No, that's the slope. Yeah, the slope is very large. Actually, the derivative is 1 of x. When x getting close to 0, 1 of x is close to infinity. So the line is more vertical. But when x increases, like x equals to 1 million, 1 trillion, 1 billion, and the derivative is going to be 1 of x, it's getting smaller and smaller. So the curve nearby infinity is almost a horizontal line. Right? It's harder to imagine, right? If you look at local picture, you cannot see that. Right? That is why we needed to analyze data and because we cannot draw the whole picture, but still want to predict something in the future. Right? So you have to, without many problems, mathematically related problems. We call it modeling, mathematical modeling. Yeah. For example, we have to maybe research project like based on current data. Can you predict? Are you going to get 4 months of Social Security when you retire? Okay. And you find out if the government cannot do anything, you can provide the data to the government. Say, hey, in the future, 30 years later, those people on the paper, every time when you receive the letter, right, from a Social Security, when you retire right now, you will get so much money. But when you really retire, that time, if the government cannot do anything, and mathematics can show you, you can only get like 60% of what is printed on the paper. So there's no money there, right? And so you have to do something on that. All right, so this is a formula. All right, then if you look at the absolute of x, natural absolute, it's defined for negative x. So the question is, what is that derivative? Then you have this function is not defined as the origin, but it's defined on the left-hand side, the x-axis, and the right-hand side x-axis. So there's 2 cases here. So if x is positive, natural of x is going to be absolute x is going to be natural of x, right? So the derivative, the derivative is going to be It's going to be the itself, natural x, which is 1 of x. Okay. Now, what happens if x is negative? If x is negative, this is going to be negative x. Why? Because if the number is negative, the absolute value of that number is going to be the number without the negative sign. But x, the negative sign of x is invisible, right? We just assume that x is negative. How to get rid of the negative sign? I just put a negative sign in front of it again. So it's like a chemical reaction that kill it. The negative sign, invisible negative sign. So negative x becomes positive, okay? Without, yeah, this is the positive. So that's why absolute x is going to be negative x. But that doesn't mean this number is negative. It's positive number because x is negative. All right. Then you differentiate. When you differentiate, use a chain rule, you put a negative x into the denominator. Then you differentiate negative x. That's going to be negative 1. So the answer is still x. Because negative 1 over negative x is going to be 1 over x. Now, this time, looks like, yeah, no sign there, right? But this is negative, remember. Okay, this is negative. X is because x is negative. But if you want to write a formula, you can put together. This is as long as x is not going to be 0. So this is a formula. Right? All right. How does the graph look like? The graph looks like the graph of y equals absolute of x, natural log of absolute x looks like that. So this is a graph. This is a graph. Y equals natural. Okay, it's not defined at origin. One side is decreasing, other side is increasing. It's two pieces here. So the derivative here is negative. The derivative here is positive. Okay, the slope is going to be 1 over x. In this case, it's positive. Slope of tangent of x. Okay. Now, because of this formula, I can, if I ask you to find the antiderivative of this function, what do you have to put there? You cannot just put the natural log of x, because I do not specify the value of x, the sign of x. X could be negative, could be positive. So you should write x natural log of absolute of x. Unless I specify that x is positive. 1 of x is defined on the positive side of x-axis. Then you just put the natural x. Otherwise, in general, you should have a natural log of absolute x plus c. All right. And sometimes, if you have modified the function a little bit, and I think this, you can use you can use substitution. Right? You can use a substitution. U equals x minus k. Then that's 1 over u du, right? Yeah, du equals dx, 1 of x minus k. Yeah, this can be natural log of absolute u plus k. And we're done. So you just needed to put x minus k into the natural log to get the antiderivative. However, this is not going to be natural log y plus c, okay? I don't have such formula there. For example, I don't have, this is not going to be You cannot just move the term in the denominator. Move the term from the denominator and put it in. Right? As a matter of fact, the integral 1 of x squared is going to be negative x to the negative 1. So think about that. This is going to be x to the negative 2 dx, right? This is going to be negative 2 plus 1, x to the negative 2 plus 1 plus c. And that's going to be negative x to the negative 1 plus c. That's going to be negative 1 of x plus c. Right? That is what we learned in Math 165. So you have to pay attention to the variable, okay? Integral 1 over y dx with respect to x, there's no, it's with respect to x, not with respect to y. So it's not going to be natural log of absolute y plus c. Now, if I change the variable, then this is correct, okay? So this is the integral with respect to y variable. All right. All right, so let's take a look at the next problem. And I remember this is a problem on the test. All right. You can do like this, even make it, yeah. So I can increase the value. So right now, just x times, increase the power, right? So right now the power is 1, natural x to the power 1. Okay. All right. Yeah, think about it. All right, so how do you do it? I'm going to simplify it, right? I'm trying to find a substitution to simplify. So I don't like natural log in the denominator. So I'm going to let u to be or let y, doesn't matter, to be natural log x. So dy is going to be dy over dx, okay? That's a standard way we do when you do the substitution. So that is the derivative with respect to s is 1 over x dx. All right, so when you look at this here, it's going to be natural log of x, and here dx over dx, right? So dx over dx is going to be just dy. All right, so then it's natural log of y plus c. And what is y? Y is going to be natural log of x. So we are done. And this time, x must be positive because natural log of x is in the denominator of the original function. But the natural log of x could be negative, okay? So here, x is positive, must be. That's clear, just from the original formula, a function. But we also have to be very careful. Natural log of x cannot be equal to 0. Okay, that means x cannot be, it's the same as x cannot be equal to 1. Right? X cannot be equal to 1. Because when x equal to 1, natural log of x is going to be 0. So that function is not defined. All right. So I think we should better to put a note here. X cannot be 1, x greater than 0. Okay. Yeah. that's a remark. Now, if I increase the power to power k, k is any number greater than or equal to 1. What I can get? I can let k to be 2022. I can let k to be 3, could be 5, and then put the problem on the test. Okay, but that the method is the same now, so you can solve the problem. Just use a substitution, right? Okay, it's gone, right? When I was talking. All right, so we try the substitution. Let y to be natural x, and then dy equals 1 over x dx. That's what we learned. Okay, so I put it back. So this is going to be integral. I think it's a y to the power k and the dy, because x over dx. dx over x is going to be dy. All right, so how can I evaluate this? This is a power function, yes?
I missed it. How did you get dy equals 1 over x?
Oh.
I saw you do the last row.
Yeah. So if we have function y equals f of x, okay? Some function, okay? That's the relation. We have two variables related. dy by definition is dx dx, okay?
Oh,
that's a channel. That's kind of a channel, okay? Yeah. Now it's harder to understand what is dx here. Okay, what's the meaning of dx? Yeah, but that works very well. So that is then the derivative of this f prime x dx. Okay. Yeah. In general, we cannot separate dy from the integral. This is just part of that. When you separate, it's not going to be alive. Just like you cannot separate your nose from your body. Not there must be attached together. This is integral is, just like a dy over dx. This is just whole part. This is a derivative of y with respect to x. Okay. And sometimes for convenience, I just put a dy and over here. Right. But then you will view this like a division here, right? It's quotient. It looks like a dy divided by x. Yeah, you can view it like that. Formally, we call it formally. Right? What's the real meaning dy over dx is the derivative y with respect to x, and that is the rate of change of the quantity y with respect to x. But yeah, I have to go over this. But you can also formally view it as like a dy over dx, and then if you have another parameter, right, this will be dy over du and the du over dx. Think of it. So if you view the derivative y with respect to x as like a fraction, dy divided by dx, then this channel, it's easy to understand the channel, just cancel du and you get it back. Okay, that's a change. Okay, so yeah, this is a u, okay, u and the u. And also if y depends on t, x depends on t, you can also write as dy over dt, then dx over dt. That's another formula, right? So first of all, you have two variables, y depends x. Now you have three variables, both y and x depend on t. And then you can compute dy over dx by this one. Okay, you can differentiate y with respect to t, differentiate x with respect to t, then you look at the quotient. All right, so that is about the derivatives and differential. Okay. Then I'm going to, yeah, then you see this is going to be, go back. It's going to be y to the negative k dy, right? And according to our formula, this is going to be 1 over 3 y to the 1 minus k and plus constant. And you can write down antiderivative because k is not going to be 1. That's why you can use this formula. And this is natural x 1 minus k plus constant. Okay. Yeah. So dy is called the differential of the variable y. Now, how do you define? I don't know. It's in mathematics, it's not d times y, it's differential y. It's tiny bit of change in the variable y. Okay. And dy over dx, that's called the derivative of y with respect to x. Product for the differential also. Right, we have product for the differential also. Right. If you have two variables, d, u, and the v, two quantity here, u times v. Maybe that depends on time t or depends on x. But this is going to be du times v plus u times dv. Okay, that's a product rule. If it's easy to understand, if both are function for x, then you know that, right? You have the product rule for the, this is product for the differential. The product for the derivative would be like that. Okay. This is one we're familiar with that, right? If you have two functions, u, v, a function for x, and the product of two functions, when you differentiate the first one times the second one, you differentiate the second one times the first one. That's called the product rule, right? So I'm going to use a product rule for the differential. I'm going to put integral on both sides. Oh. Yeah, let me erase this first. Now, the fundamental theory in the calculus is like that. Integral of any variable, yeah, this one. Okay, it's going to be x plus c. Right, so this is the simplest formula. Okay. Or the integral of 1 with respect to x. Okay, so now I can differentiate. Okay, I can put both sides, right? I put integral. So the left-hand side is going to be just u times v, and plus some constant. And I switch the order here. So I get a formula called integration by parts. So if you want to integrate u with respect to v, I can switch the order and plus, okay, I'm going to, yeah. So I move the term u and the v, this integral. Now, I don't want to put a constant there because constant is already contained in the second integral v. So that's why I don't put a constant there, because this indefinite integral always has a constant there. So there's no need to put a constant here. So this is the formula for the for the integration by parts. And the uv are functions of some variable. We don't know that. Okay. All right. So where we can use this formula? Well, for example, integral of a natural log of x dx, right? I look at this integral. I want to find the integral. Find the antiderivative of this function. How can I find it? I search all the formulas, right? We learned before. No clue. Right? This is a inverse function. We just understand a little bit about this inverse function. I cannot, I know the derivative natural of x. That's the only formula I know. Right? But right now, I'm talking about the integral. So what I know is, so that's all 1 of x is going to be natural of x plus c if x is positive, right? So that's what I know. But the integral here is natural of x, right? So I have to do something in order to solve the problem. What I'm going to do is I'm going to let u denote natural of x by u. And then u has a u and v, right? V is x. So what I'm get v is x, okay? Right, u is going to be natural of x. So what I'm going to get u times v minus x and the du. Du is the derivative of nature of x times dx. So just 1 of x dx. Okay? All right? Because u is going to be natural of x, I just mentioned that du is going to be the derivative of nature of x. X. Okay, so after simplified, you get 1. And the integral of 1 is just equal to x. And then you have to put a constant here. So that is a, okay, that is the antiderivative of nature of x. Believe it or not, we can check that. Right? We can check. I can check. I differentiate. I want to see if I can get a nature of x. First of all, you apply the product rule to the first one. So it's going to be 1 of x times x minus a plus natural log of x times 1 and plus 1. So after you simplify, you only get natural x. Yes, this is the indeed. Okay. So find the antiderivative is the inverse procedure, right? It's harder to figure it out without using the partial integration by parts, the antiderivative of natural of x. Right? How do you know that, right? Natural x, the antiderivative. That's a part, yeah. That's the inverse problem. You see the result. You want to get the original function whose derivative is going to be natural of x. This is just like a solve a differential equations. Yeah, it's not easy to solve differential equations. If you will deal with lots of differential equations if you measure the electronic engineering, right? So I don't think I'm not going to have a time. They are going to discuss this type of ideas in the next class. I'm stopping here today. It's a real quiz.